Welcome back to the lecture on pH. Let's talk about that. Go back to our notes here. All right, before we were talking about the basic definitions and how water can be both. Let's use that water to talk about what in the world is pH and pOH. In a nutshell, it is just trying to get away from really big numbers or really small numbers. And the little p right here just means I did a mathematical function. And this mathematical function means I took the log and multiplied it by a -1. Okay, that's all the P stands for. So you could take the, I don't know, the P log. What in the world would be a P log? It would be the negative log of the log. Okay, there's nothing special about that. It's just telling you that I did some math. So pH means I took the negative log of the proton concentration. The reason we do this is it gives us larger numbers, and those are usually easier to visualize. So a pH greater than 7 would be considered basic. A pH exactly equal to 7 would be considered neutral. And a pH of less than 7 is going to be considered acidic. All right, it's a kind of a backwards deal. So keep in mind, if the proton concentration is 1 times 10 to the minus 7th, if you take the negative log of that, now some of your calculators might give you an error on this, but it should come up to be 7. Oh, that's not acidic or neutral, or sorry, acidic or basic. That one's neutral. Yes. So when you see a pH that is less than 7, that means the proton concentration is greater than 1 times 10 to the minus 7th. Okay, kind of a little backwards thinking there, but pH kind of switches it. So if you see a pH that's greater than 7, that means the proton concentration is less than 1 times 10 to the minus 7th, or it favors the hydroxides. Now, of course, there's nothing wrong with taking the pOH. It's just the negative log of the OH, and your numbers are going to be very similar, but a pOH of greater than 7, in this case, is acidic. 7 is still neutral, and a pOH of less than 7 would be basic. Most people like to just consider the pH aspect, but if you have a pH, you always have a pOH. And then there's a wonderful, wonderful relationship where if you take the pH plus the pOH, it is going to equal the big number 14. Oh, if you know one, you will always know the other. Always, always, always. I'm going to switch over to the whiteboard. All right, so this is what I had written for the water. I wonder if I could take the negative log of this thing. Why, sure. If I took the negative log of Kw and the negative log of the proton and the hydroxide, so I'm just taking the negative log of both sides. Now I know this number is 1 times 10 to the minus 14. So the negative log of that turns out to be 14. And this would be the negative log minus, see if I'm doing my log rules right. It's been a while. All right, so 14 is equal to the pH. Oh, I don't know why I did minus. This is multiplication. Plus, and negative log of OH is pOH. And that's where that equation comes from. Okay, there's nothing tricky to it. I literally just took the negative log of both sides. Now, beware, if you haven't played with pHs a lot, pHs can be less than 0. Okay, so you can have a pH in the negative range. That is okay. And you can have a pOH greater than 14. It's just water generically by itself gives you that 14 unit range. So don't freak out if you see pHs that go negative or if pHs go above the 14. Ah, what is pH? The little p stands for negative log. What is the negative log of? Of the proton concentration. Why do we use it? We just tend to like numbers like pH 14, pH 10 a lot better than the numbers 1 times 10 to the minus 10th or 1 times 10 to the minus 7th. All right, let's just do a couple calculations. All right. If I have a proton concentration of 2.3 times 10 to the minus 4th, I want to know what the pH is. I want to know what the pOH is. I want to know what the hydroxide concentration is. If you know one, you know all four of them. All right, there's a couple ways I can do this. I'm going to do the pH first. So I'm going to take the negative log of 2.3 times 10 to the minus 4th, and I'm going to calculate that out. And 2.3 to the negative 4th, and make sure you take the log base 10, not the natural log, and this comes out to be a negative 3.64. But, a negative and a negative, okay? So the pH is equal to 3.64. Yes, you can have negatives, but I had to multiply the answer by a negative 1 because that was part of my equation. All right, let's talk about sig figs for a minute. For logs and natural logs, the total number of significant figures goes behind the decimal in the answer. So this had it had 2 total sig figs. So my answer gets 2 places after the decimal. Now we're just going to get it back out just to make sure that we can. All right, so if my pH is 3.64, 3.64 is equal to a negative log of the proton concentration. Okay, I'm trying to find the proton concentration, so is it by itself? No. So I'm going to multiply both sides by a negative 1. And then the way you get rid of a log is to do an antilog, and this is base 10, and what you do to one side, you do to the other. And so my proton concentration is 10 to the negative 3.64. And this is the use of that button that you all wanted to use when we were doing scientific notation. This is actually the log button. And plug it in. This has 2 after, so it's going to give me 2 total, and the rounding might be a little bit different. Let's see, function, and my calculator was still carrying the answer, so I get 2.3 times 10 to the minus 4th. Don't forget your unit. Don't forget your unit. All right, so that's how you would get into the pH and out of the pH and with the sig figs. Well, what if I want the pOH? Well, I already have the pH, so let's just do the simple route. Because I know the pH plus the pOH is equal to 14. So if I have 3.64 plus the pOH is equal to 14, and remember that 14 is sig figless. So 14 minus 3.64 is 10.36. Oh, nice. All right. So I know the pH, 3.64. I have the pOH, it's 10.36, and then I need the hydroxide concentration. And there's a couple ways I can find this. I have the pOH, so how about I just do the anti-log back out? First of all, multiply both sides by a -1. And if you want to get rid of a log, do the anti-log. And so the hydroxide would be 10 to the negative 10.36. There's 2 after, so my answer should have 2 total. And 4.4 times 10 to the minus 11th. Don't forget your unit. We're back into molarity. Oh, well, how else could I have found that? Well, don't forget we also know this. 1 times 10 to the minus 14th is equal to 2.3 times 10 to the minus 4th times the hydroxide. And guess what? Sometimes there'll be a little bit of rounding issue, but we will get the same answer. 1 to the negative 14th divided by 2.3 to the negative 4th. Oh, look, the exact same answer. It does not matter which way you go. If you know one, you know them all. All right, pH versus pOH. Why in the world do we call them pH and pOH? Because we did the mathematical function of taking the log base 10, and then we multiplied that answer by a -1. Why? So that we had larger, nicer, generally positive numbers to discuss. Then we can kind of look at this scale. pHs, which are greater than 7, are basic. pHs that are 7 are neutral, and pHs that are less than 7 are considered acidic. We can do the same thing with pOH. It's just the other side of the coin. And we have this wonderful relationship where pH plus pOH is equal to 14. But do not forget that originally came from this identity. There's nothing going, there's nothing wrong with going back and using your equilibrium expressions. Oh, okay. Well, do you have some pHs of some common items? At the very beginning, I believe it's in the green pages, I actually have a whole bunch of common, but I will talk about that when I deal with the strengths of acids. All right, until next time, Jolly out.